And action potentials, hooray! All right, this video may be a little longer because I don't want to cut it off in the middle. And this is going to be one of those times it's an advantage that we're online and you're just seeing this because some people have trouble with this and you can watch the video again and again rather than just trying to gather it all in class. So let's talk about action potentials. Nerve cells are excitable cells and they communicate. And they communicate by a change in the membrane potential. That voltage is going to go from minus 70 millivolts. All of a sudden, it's going to get positively charged and then back down again. So it's going to be due to a brief change in permeability. So all of a sudden, sodium can rush in through voltage-gated channels. Not rushing in through the passive pores, but it can rush in, and for a millisecond, literally a millisecond, the neuron is going to be positively charged inside. So what an action potential is, for a brief period of time, the inside of the nerve cell becomes positively charged compared to the outside. Remember, it was negative. It was minus 70 millivolts. But all of a sudden, sodium rushes in, and it's going to become positively charged. So it goes from minus 70 millivolts all the way up to positive 35, plus 35 millivolts. And then it's going to go back down to minus 70. And actually, it's going to get even a little more negative than that, go to about minus 90. And why this happens, it's due to a change in the permeability of the membrane to sodium and potassium. And voltage-gated sodium and potassium channels are going to open and close. Let me give you some terms. Let's start with some terms. This, first of all, is your basic action potential. And it always looks like this. You don't have ones that are wider or flatter or taller or smaller. This is it. It's all or none. It looks like this. Here we are at rest, down here at minus 70. This upswing, when we're going more positive voltage, that's called the depolarization. And they call it that because as you get closer to zero, it's actually, and then it gets polarized again, but we call this whole thing a depolarization. That's when it's getting more positive. And that's when sodium is rushing in through the voltage-gated channels. Repolarization is when we go back to where we were at rest. We go from plus 35 down to minus 70. Hyperpolarization is, look here, it gets even more negative than we were at rest. It goes down to about minus 90. That's hyperpolarized. And then we go back to rest. So let's also review some channel types. Now we've already talked about the passive pores. Those aren't doing anything. Those are always open. They just are what they are. And sodium's going to rush in through the passive pores and sodium ones, and potassium's going to rush out through the passive potassium pores. But let's talk about the voltage-gated channels. Two main types we'll talk about. Voltage-gated sodium channels. There's two parts to it. There's a fast gate, and at rest, that's going to be closed. Now I'll go through this. And a slow gate, and that's going to be open at rest. And it expands the membrane, and it's going to allow sodium to rush into the cell. So this is the fast gate. This is considered the slow gate. And I'll go through more. Potassium channels, thank goodness, are easier. Potassium channels are either, voltage-gated channels are either open or closed, the end. So here it is. If they are open, then potassium rushes out with its concentration gradient from in to out of the cell. At rest, these voltage-gated potassium channels are closed. So here's our basic cell. And these are the pores. Sodium pores or passive channels are always open. Sodium rushes in. Potassium pores, the passive channels are always open. Potassium is going to rush out, and there's more of these. So it's easier for potassium to rush out, but they're always there. Let's ignore them and talk about the voltage-gated channels. All right, voltage-gated channels, there's a fast gate and a slow gate. At rest, for sodium, the fast gate is closed. So imagine it's a door with two locks on it. If one lock is locked, you still can't get into the door. Both of these locks have to be open. So at rest, sodium can't come into the cell through these voltage-gated channels. Potassium voltage-gated channels are also closed at rest. So potassium can't get out. Did I say that sodium can't get in? Potassium can't get out. When they're open, Potassium rushes out, sodium rushes in. So let's go back and look at the sodium channel in more detail. So there's two gates, a fast gate and a slow gate. At rest, the fast gate is closed and the slow gate is open. But there's two locks on this door. Both have to be open in order for sodium to cross the door, to get into the cell. So what is going to open up the fast gate? It's voltage gated, meaning it has to hit a certain voltage, and that's minus 55 millivolts, to open up this fast gate. Hitting minus 55 also is going to start this guy's closing. So at rest, fast gate is closed, sodium can't get in, even though the slow gate's open. But when you hit minus 55 millivolts, the voltage that opens up the voltage gated channel, the fast gate opens up, sodium can rush on in. Right? At the same time that this guy opens, the fast gate opens, the slow gate gets the signal to close, but it's slow. And so it's going to take a millisecond or two until it finally closes. Once the slow gate closes, sodium can no longer come in because it's a door with two locks. It was that this one was locked and then it opened, but now this one's locked. You can't get in anymore. And just, I do have a trivia about voltage-gated sodium channels. I don't know if you've ever heard of tetrodotoxin. It's a poison that's in pufferfish, and it's one of the more potent toxins in the world. How it kills you is tetrodotoxin blocks voltage-gated sodium channels. So your nerves don't work, so you can't send a signal on any of your nerves to make your muscles contract to do anything. So that's how tetrodotoxin will kill you. It blocks voltage-gated sodium channels. There are other toxins. Scorpion toxin actually prevents the activation. It keeps them open, and that's bad as well. All right, moving on. Voltage-gated potassium channels are simpler. These are also slow. They're closed at rest, and hitting the magic voltage, hitting that depolarization of minus 55 makes them open, but it does it slowly, relatively slowly. It's a millisecond. But so here it is at rest. Potassium cannot get out of the cell until you hit minus 55, and that's going to give a signal to open up this channel, but it doesn't happen immediately, it happens slowly. But then, so after a millisecond, it's open, and potassium can now leave the cell. But I changed my mind. I'm going to close this one out now. I'm going to do a couple shorter videos. So this one will just be on the voltage-gated channels. The next one I will cover action potentials.